So one crucial element of the vision we have for this program is finding people who are extremely talented but may not have spent a tremendous time working on the climate issue, but that have great education, great work experience. And this climate problem is so urgent and so complex that it really requires the best and the brightest from all sorts of disciplines to find it and then excel in it. And I think we were extremely lucky to have Emily apply to this program. She's worked as hard as anybody who's ever been in this program, and the quality of her work has been outstanding. And I've really enjoyed having her in the program as well. I'm probably going to say that about everybody this year, but really a phenomenal job from start to finish for Emily. And her topic is going to be waste to hydrogen, another capstone that I advised and I'm very proud of. So Emily, the floor is yours.
Thank you, Corey. Hi, I'm Emily Grady, and my capstone is on waste to hydrogen. So a quick overview of what this presentation will go over. First, I will do a full overview of waste and how we conventionally manage waste in California, and then we'll go into waste to energy technologies that we use today, along with some emerging pathways that we can recover waste from energy or recover energy from waste but aren't currently using. So this is also known as transformation, and waste to hydrogen is just one subcategory of waste to energy. So when I talk about waste to energy, that's sort of the broader umbrella of which waste to hydrogen is one of them. So then we will go into hydrogen. Why do we care about it? What does the current market look like? And what are projections for the future market? And then into some of my conclusions of what are the viable pathways to recover energy from waste, hydrogen from waste, and a case study that I did in Los Angeles, along with some recommendations. So landfills are the conventional disposal method for waste. They come with a whole host of problems, from land use to toxic emissions that stay in the local community, and they're also the source of 20% of methane emissions in California. So we can capture some of this methane to use it as renewable natural gas, but that's really the only positive thing that can come from landfills. And municipalities will pay tipping fees up to $150 per ton to dispose of waste in both public and private landfills. So obviously landfill diversion is a huge priority, and recycling is the top of the hierarchy when it comes to diverting waste from landfills. However, due to changes overseas in the market, the value of recyclables has decreased, leading to a decrease in recycling rates over the last few years. And this just leads to more plastics and recyclables going to landfills and ending up in oceans and lands. So finally, composting is organics recycling. And this is essentially just making a very high nutrient mixture that you can add to soils for organic farming. And it's a much smaller piece of the pie than landfilling or recycling, but it is another conventional management method. So in addition to disposal and recycling, we can also recover energy from waste. So one way that we do this is through anaerobic digestion. And essentially, this is just putting biomass into an anaerobic digester. This produces biogas, which you can further process into biomethane, which you can use as renewable natural gas. And this is most commonly used as a transportation fuel. And it does produce emissions, as Kate mentioned in her presentation, when you actually consume it. However, the actual anaerobic digestion process isn't super harmful, especially in the local community. Unfortunately, with incineration, we cannot say the same thing. So this is just the mass burn, usually of municipal solid waste, which is essentially just mixed garbage that you would throw into your garbage and would normally be sent to a landfill. And this is burning the waste to produce steam, to drive a turbine, and make electricity to send to the grid and power homes. So in addition to the electricity, there's also flue gas released from these incinerators, and this has a whole profile of emissions from greenhouse gases to carcinogens, most notably dioxins, which is a carcinogen that stays in the local community. So we have huge environmental justice issues with these facilities, and they're just massive facilities that burn a ton of waste. So it's just a really outdated form of electricity production, and we have cleaner ways to make electricity. So there are 2 remaining incinerators in California, and we'll come back to this a little bit later in the presentation as well. So some of the pre-commercial pathways that we're not currently using at scale to produce energy from waste is thermochemical conversion. And this is often grouped together with incineration, with public perception of what this technology is. So I'll go a little bit further into actually explaining the process. I'll focus on gasification because it's so much further along in the development than pyrolysis is, but they're very similar pathways. So essentially with gasification, and we'll focus here on this pathway to produce hydrogen, you put a feedstock into a gasifier, which is just a high temperature, high pressure environment, and add a little bit of oxygen to produce steam. And this makes syngas, which is basically just a mixture of carbon monoxide and hydrogen. So this is the really big difference between incineration and gasification, is that this syngas is not combusted, and you can actually clean it before it becomes a gas that's released into the atmosphere. So with incineration, you're scrubbing the toxins out of a gas that's already being released into the atmosphere. And this one, you have a higher potential to actually clean up the syngas before you turn it into useful energy. So when you want to make hydrogen from syngas, you put it through a water-gas shift reaction, purify it, and that generates hydrogen. And we do produce hydrogen through this process today, just not using waste. So about 23% of hydrogen production is gasifying coal as the feedstock, and you can use biomass and municipal solid waste. We just haven't yet demonstrated that yet at scale. So first, why do we care about hydrogen? It's the most abundant element on the planet, and it's an energy carrier that only emits water vapor when it's consumed. However, it's only as clean as what we use to produce it. So since hydrogen is naturally existing as a compound where it's actually attached to another molecule, we need to extract that from the molecule. And I have two really simplified reactions here just to show you two different ways that we can make hydrogen. The first here is from natural gas, which is full of methane, which is CH4. So if you put this through this simplified set of reactions, then you see that we have our hydrogen yield here, but we also have carbon dioxide emissions that are emitted into the atmosphere. We can also extract it from water. So if we want to split this H2O using electricity, then you get hydrogen, and the only byproduct is oxygen, which is not a greenhouse gas and is not harmful. So today, the global demand for hydrogen is 70 million metric tons, and over 95, but really closer to 99% of that is produced using natural gas and coal. So this has a carbon impact of 10 to 20 kilograms of carbon dioxide for every kilogram of hydrogen that's produced, and that leads to 680 million metric tons of carbon dioxide equivalent emissions annually. And to put that into perspective, that is greater than the emissions from the country of Germany in an entire year. So this is a huge polluting industry. It's mostly used for petroleum refining and ammonia production used for fertilizers. But because of these characteristics of hydrogen, that it doesn't emit any harmful greenhouse gases when it's actually consumed, and it's an energy carrier, it's being considered for a lot of different applications when it comes to decarbonizing energy. So first, for a fuel for difficult to decarbonize sectors like steel and cement, where you need really high temperatures that you just can't get with electricity, hydrogen is one of the only options that we have that is not a fossil fuel to get these high temperatures to make steel and cement. Additionally, with heavy-duty transportation, we know that electric vehicles are very common for transportation in general, but like Kate was just talking about with the weight of batteries, it doesn't make sense for heavy-duty transportation in planes, so hydrogen is also being considered for this. And third, for seasonal energy storage, where you have a region that doesn't get wind and solar for weeks on end and you need a fuel source in order to produce electricity, hydrogen is an option that is able to store energy on seasonal timescales, which compares to batteries, which is more like hourly timescales right now. So there are a lot of different applications for hydrogen in the future, but what's really important with this is that we're growing the demand for hydrogen right now, but we're not yet transforming the way that it's being made. So we have ways to make hydrogen without any carbon emissions, and this is called green hydrogen. So if you split water using electricity that's just powered by wind and solar, then this can make hydrogen with no emissions, and this is called green hydrogen. But this isn't currently cost competitive with brown and gray hydrogen made with fossil fuels. So when it comes to this market, we really need to reduce uncertainty to spur more investment in the green hydrogen and the zero carbon hydrogen methods so that we can increase the supply and demand, reduce market uncertainty, and eventually get to this future of zero carbon hydrogen for decarbonization. So this is where the waste to hydrogen comes back in. Essentially, this can leverage a future hydrogen market because of economics. So with waste to hydrogen processes, and most specifically like gasification and thermochemical conversion, if you have a gasification plant then that plant will be paid to actually take the waste, similar to how municipalities will pay tipping fees to landfills in order to take the waste and process it. And then they also have downstream revenue when they're actually selling the hydrogen. So if you compare this to other types of hydrogen production, you're only really making revenue when you actually sell the hydrogen. So this, we have leverage both upstream and downstream. And so some pathways that we can use to generate hydrogen from waste. One is more indirect, where it's just biomethane reformation. And if you remember our anaerobic digestion, that biomethane is really just renewable natural gas. So you can use the same process as we do natural gas right now and reforming that. So you can get the biomethane either from anaerobic digestion of biomass or from landfill gas capture. And then second, with thermochemical conversion, that is what we talked about with gasification, producing hydrogen from waste in a gasifier. And you can see here, this supply curve is initially starting out with biomethane reformation, and then thermochemical conversion really starts to take over after 2030 in complementing green hydrogen for the supply and meeting this growing demand. So one thing that I really wanted to do with my project was try to make some quantifications of being able to compare different disposal methods. And Los Angeles County provides a really good case study to actually do this. One, because their landfills are reaching capacity. So we have maybe 10 or 15 years left until there will be a real crisis there with landfill capacity. And second, because there's currently an incinerator in Long Beach, which is part of Los Angeles County, called the Southeast Resource Recovery Facility. And that transforms 368,000 tons of waste per year. So while this isn't a clean way to make electricity, it also is diverting waste from landfills that are filling up in Los Angeles. So what this is phasing out within the next 10 years, but most likely in the next 3 years when their current contract ends. So one of the plans that LA has right now is hauling waste by rail 210 miles into the desert to the Mesquite Regional Landfill that's already been built but isn't yet being used for disposal. And so this just has a ton of greenhouse gas emissions, lots of cost with transportation, and also pollution just from, by nature, hauling waste into the desert, 210 miles. So my idea here was to think of like a cost-benefit analysis for a gasification plant in Los Angeles that would, instead of sending the waste that's now going to the incinerators once it phases out, instead of sending that to the landfill, sending that to a gasifier and see how that compares in terms of emissions, in terms of cost. And so we were able to quantify some of this, but just because of lack of data, mostly when it comes to the greenhouse gas emissions, both from landfills and gasifiers, we weren't able to get a simple net present value from this just because of so many assumptions that I had to make when making these calculations. It didn't really make sense. But one big takeaway that I got from this was just further reiterating the point of how different incineration is from gasification. So even though these are often grouped together as just waste to energy processes, the gasification plants are so much smaller in scale, especially the ones that are being marketed right now, that on one hand, they don't have the same diversion impact that the Southeast Resource Recovery Facility would have. So a 24-ton municipal solid waste gasifier would produce 1.2 to 1.5 tons of hydrogen each day. And this is only 2.25% of the total amount of waste that's incinerated at SURF every year. However, this is also enough to fill up 280 hydrogen-powered cars. So while this isn't having the same diversion impact by just putting in one gasification plant, it also isn't having the same local impact in terms of emissions, in terms of local pollutants and toxins, just because the scale is so much smaller. And you can actually put this in like a waste transfer station or next to a landfill so that you're not having all of these logistical issues that you have with incineration and transporting the waste to these huge facilities. So on one hand, with the waste management, having one gasifier doesn't make a huge difference, even though it is still getting waste away from landfills. However, it does make enough hydrogen to make this something that should be considered. And it also isn't having as much of a local impact on the negative side either because they're so much smaller. So coming to my recommendations in conclusion, my first recommendation is sort of spurred from the fact that I really couldn't get very reliable data when it came to methane emissions from landfills, and we now have tracking satellites that you can get more accurate methane emissions from their point sources. So one of my recommendations would be to use these satellites to get more accurate information on methane emissions from landfills. And I think that this is especially important when it comes to municipal solid waste and non-recyclable plastics, where you don't have the options to do anaerobic digestion because those only take biomass. And so being able to actually compare an alternative technology like gasification to make more informed policy decisions about what should be incentivized and what should be included in certain definitions or policies, I think should be really important. And then second is modifying the definition of gasification. So the definition itself is very strict, which is one issue with it, but on a broader scale, the definition limits what gasification is considered to be as producing a clean burning fuel for the purpose of generating electricity. And this is pretty backwards just because we have cleaner ways to make electricity right now, but we aren't currently producing hydrogen in cleaner ways than this gasification option. So when it comes to the definition, hydrogen definitely should be included in there in order to have at least a chance for this developing technology to prove itself as a way that we can produce hydrogen from waste, so that it is at least on an equal playing field with other diversion technologies and can complement recycling, composting, anaerobic digestion, and other possibilities. So that's my presentation. I just wanted to thank my Capstone committee. Everyone was extremely helpful, keeping me on track throughout this research process. So I really appreciate it. And now I'll take questions.
Excellent job, Emily. This first question, I promise, is not from me, but ironically, I did put a comment in one of your drafts that sounds a lot like this question, so get ready. Many opponents to hydrogen question the 40% round-trip efficiency of hydrogen as energy storage. Are there any technology pathways to increase this efficiency? As a reference, the round-trip efficiency of a lithium-ion battery is on the order of 77 to 85%.
So I can't confidently answer that question just because I tried really hard not to go down too many rabbit holes in this research, and I tried to focus more on the waste side when it came to these processes. So not to my knowledge, but that's not something that I'm sure of right now.
And follow-up, if the round-trip efficiency is so low, why not just store the methane itself and not convert it to hydrogen?
So, I mean, at least in terms of waste to energy, renewable natural gas and biomethane is in very high demand right now. So that's something that's being considered for so many different options, especially with transportation and really just anything that we can use natural gas for. So that would be my take on that one.
And another question coming in here is, what are the end products of gasification of biomass, and how are they disposed of and stored?
So the gasifier that I looked at was the ways to age gasifier, and that it produces 99.99% pure hydrogen. And so that one puts it directly into fuel cells. So that would be used primarily for transportation.
All right. Any questions from the room? Kate.
I have a quick question. Sorry if this is outside of the scope. You mentioned that a lot of the plants, the gasification plants, are pretty small. Is there an appetite for a large-scale gasification plant, or do they want modular because it is so small and has other benefits?
I think the idea of the modular gasification plant when it comes to waste is that you can put these in like a waste transfer station or next to a landfill. So with incinerators, you have a lot of logistical issues. So when it comes to transporting the waste, there's a ton of congestion there. There's a lot of ash and pollution and just from transporting the waste there. So because these gasifiers can be smaller, and you can put them somewhere where waste is already going. That is really the reasoning behind the modular design, but most of them are scalable, so they can be from anything. I've seen up to like 60 tons of municipal solid waste per day. So they can get bigger, but I think the smaller design is on purpose because of those logistical issues.
Any additional questions from the room? Let me check anybody watching online right now, by the way. We have a good number of you watching. Please feel free to put some comments in the chat on YouTube. I can see those too if you want to ask a question in there. Anybody else? So Chrissy, you got a question.
Was there anything you wanted to talk about that you weren't able to put in the PowerPoint?
I would have loved to talk more about green hydrogen specifically because it is such an interesting vision for the future. So that was probably the one thing that I would have expanded on a little bit more.
All right. So great job, Emily.